Okay, Calculus Unit 4, Day 29, 30 notes. This is Part 2. So we have a problem here. Air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. Cubic centimeters, again, that's volume. 3 dimensions. So at the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? So let's go through and identify different parts of this equation or of this question, and then we'll be able to hopefully set up an equation and then talk about it from there. So down the road, we're going to have to figure out what we need to do when we know it's a shape. The shape is a sphere. Excuse me, I meant to circle the sphere. So now, what do they tell us? Air is leaking out 230 pi cubic centimeters per minute. Okay, and I said cubic, and that has to deal with volume, but that's the change in the volume. So that's the rate at which the volume is changing. There's dV dt. At the instant when the radius is 4 centimeters, so that's just the radius, which is just r. And now, what is the rate of change of the radius? That's dr dt. Okay, so now let's answer some questions, which is going to kind of teach us how we should go about solving these related rate problems. So identify all the variables involved in the problem. We're talking about radius and volume. Okay, which radius is r, volume's v. Identify which, if any, of the variables in the problem that remain constant. And that was like that example, I think it was either 3 or 4, where it said, hey, the number 4 where r is constant, and on number 3 we said where c is constant, but there's no constant variables here. Okay, number 3 asks us, and I broke these up in 2 parts, identify the rates that are given and the rate you wish to find. So what did they tell us? If I go up above, hey, they told me dV dt is equal to 230 pi cubic centimeters per minute. Okay, that's helpful. And then what don't we know? What are we looking for? We're looking for the rate at which the radius changes. So that's dr dt. Okay, and again, we don't know that. And they gave us the radius in centimeters, and a lot of times we want to keep them the same, and that's just one-dimensional, so it's centimeters per minute. Okay? All right, let's look at number 4, and I'll have to flip back and forth between these 2 screens. Write an equation, often a geometric formula or trig equation that relates all the variables in the problem for which a rate is given or for which a rate is to be determined. Well, we know in this case it's talking about volume of a sphere, so volume equals 4/3 pi r cubed. Again, substitute any value that represents a variable that is constant throughout the problem. It's important to keep in mind that you can have only one more variable than you have rates. You may have to make a substitution that relates one variable in terms of another, and that's not going to be the case this time, but we'll keep that in mind when we go forward. And I think on all these it says the directions there. Okay, so now once we have the equation, we want to differentiate both sides. We're going to implicitly differentiate both sides, and we did this one already. But the derivative of volume is just derivative of v is just 1, but then it's going to be dv dt. Pi is constant, so hey, we got to take this power, multiply it 4/3 times 3 is just 4. So we have 4 pi, and then we go down 1 power, and then we have dr dt. Okay, so I have a couple unknowns here. dv dr, dv dt, dr dt, and r, but they tell us, so there's 3 unknowns, but they tell us 2 of them. So if you flip back up or you look back up above, what do they tell us? They tell us dV dt is 230 pi cubic centimeters per minute, and the radius they tell us is 4. Now, there's one thing we've got to pay attention to here, so let's start filling in number 6. Substitute all instantaneous rates. So we have 4 pi, and we just said the radius, again, when the radius is 4, so it's 4 squared. I do not know what the change in the radius is. That's what I'm trying to find. Now, one of the things here we got to pay attention to is that the volume was getting smaller. I probably should have written this up above. So let's go back up here. The dVdt, so they're saying air is leaking out, and so if it's leaking out, it's going to be getting smaller, so it's actually going to be decreasing negative 230 pi cubic centimeters per minute. So then when I come down here and I substitute in for the dVdt, that's going to be negative 230 pi. Okay, so now let's simplify. Again, we're going to need our calculator here in a second. 4 squared 16 times 4 is 64. 64 pi dr dt. And again, substitute all instantaneous rates and values of the variable, solve for the remaining rate or variable. In this case, I'm trying to solve for my unknown, dr dt. The rate of change of the radius as it relates to time. Okay, so let's divide both sides by 64 pi. If I do to the right side, I have to do the left side. I'm going to need my calculator here. So those cancel out over here. But now, why is that nice? Because now all I'm left with is dr dt, and it's negative 230 over 64. And when I put that into my calculator, I'm going to get negative 3.594 centimeters per minute. Okay? And that is how much um, when the balloon gets to 4 centimeters, it is changing at negative 3.594 centimeters per minute. Okay, and obviously that rate's going to change as the air goes out. Okay, that's going to be it for part 2. We'll do the next one as part 3.